Hey there. I wanted to do problem 96, and I just don't think we're going to have enough time to do it in class. So here is problem 96. If you would like to get some extra credit, first of all, you had to watch this video, um, and which means you're hearing this. So if you want to go ahead and do this problem at the same time I'm doing it, and then send it to me in an email or send it to me in a text, you can get some extra credit. All right. Okay. So I don't have the very first part of this problem 96, but it said the continuous function g, okay, is defined on the interval from -4 to 10. The graph of G consists of two line segments. Okay, so I can see here's that one line segment, here's another line segment, and two semicircles. So this is a circle and this is a circle. Okay, as shown in the figure, which you are seeing. All right, so the question says, and it also says for the function f, which this is not f, this is g. They just told us that this is g. In fact, I think I'm even going to mark that. Okay, that hopefully my stylus is working. Okay, so this, oh, it's actually even marked. Right, it's marked right there. So this is g, but they're telling us that g of x is actually the derivative of f of x. So this is the derivative. Even though they're calling it g, I have to recognize that this is the derivative. Okay, so the first question says find the average rate of change of g on the closed interval from -2 to 4. Okay, well, that's just finding the average rate of change. That's just finding the change in the outputs over the change in the inputs, right? The slope. So I'm going to do that right over here. So that's going to be g of 4 minus g of -2 over 4 minus -2, which that's 6. So g at 4, let's go and find g at 4. G of 4 right here is -4. Okay, and then g at -2, let's find that. G at -2, it looks to be, it's hard to see, but I'm going to say that that's 5. They really should have it marked, but I'm going to say it's 5. Okay, so that looks to be -9 over 6. So I've got -9 over 6, which simplifies to -3 over 2. All right, so that is the average rate of change from -2 to 4. All right. No units involved, so I don't have to worry about that. Okay, so that was A, pretty easy. Okay, B, it says, explain why there is no value C on the closed interval from -3 to 0. So let's go ahead, I'm going to erase some of this so I have a little more space. Okay, so let's go ahead and look at, so -3 to 0, that would be from right here to here. Okay, so explain why there is no value C for which the derivative of C would be equal to the average rate of change, okay, of G on that interval. So this sounds to me like when I'm seeing a derivative being equal to the average rate of change, that is the mean value theorem. So explain why there isn't one. Well, that must mean that the conditions to use the mean value theorem is not being met. And when I look at it from -3 to 0, I can see that right here, the derivative does not exist, okay? So remember to use the mean value theorem, it has to be continuous, which it is. I can see it's continuous, but it also has to be differentiable on that open interval, and it's not, okay? So I'm not gonna write that down, okay? I'd like you to put that kind of in your own words, but that would be explaining this, explain why that does not contradict the mean value theorem. So let's look at, actually though, I still need to explain why there's no value C. So let's look at it. So G prime at C according to the mean value theorem, okay, even though I know, right, it doesn't contradict it because we can't actually use it here. But the mean value theorem would say that the derivative at G would be equal to the average rate of change on that interval, which would mean G of 0 minus G at -3 over 0 minus negative 3. So what is g at 0? Well, g at 0 is 0. What is g at negative 3? Well, it's 0. So I'm basically getting 0 over 3, which is 0. Okay. But when I'm looking at that, right, I can see that there's the only point, okay, so the derivative, right, the instantaneous, the average rate of change is 0. That means there has to be an instantaneous, right, or the slope of a tangent line would have to be equal to 0 on the interval from negative 3 to 0. The only place where that could possibly happen, because this is a line, right? It's got a positive slope going up. This has a negative slope going down, would be right here, right? Kind of where my cursor is circling, but there's not, the derivative doesn't exist there. Okay, so that's why there's no value C. Okay, it doesn't contradict the mean value theorem because we actually can't use it on that interval. All right. Okay, and let's look at the next part. Okay, so part C says, again, on a closed interval from negative 4 to 10, find the critical numbers of the function f. Okay, identify each of these critical numbers as corresponding to a local min, a local max, or neither, and justify my conclusion. All right, so again, I'm not going to write everything out here because you're going to get some extra credit, all right, if you do it. So we need to find so critical numbers of f means when the derivative of f, which is actually this function right here, g, when does it equal 0 or when is it not defined? So I'm going to go ahead and just kind of circle some of those places. So where is it? Well, right here, right? Right here, the derivative is 0, so that's at negative 3. Right here, the derivative is undefined because it has that sharp curve. I shouldn't even say it's not curve, has that sharp corner. Okay, that's more appropriate. It's also 0 at right here. Okay, right here it's 0. And it's also 0 right here and right here. Okay. So those are the possibilities, okay? So how would I know that they're local max or mins? Okay, well, I'd have to look at, does the derivative change sign, right? So I'm noticing that right here, the derivative is negative, and then it goes to positive. That means that it was decreasing and then increasing, so this must be a local minimum point. Okay, this point up here, well, the derivative is positive on both sides of it. Okay, so this is neither, right? And again, my justification, when I write down my justification, I would put this is not a local max. It is a critical number. It's a critical number, but it's not a local max or min because the derivative is positive. Okay, it doesn't change sign. Okay, this one is a local min because the derivative changes from negative to positive. This is a local max because the derivative changes from positive to negative, meaning it was increasing and then decreasing. Okay, this is nothing either, okay? Is this a local min of the derivative? Yes, but not of the original function. Okay, and this one right here, it changes again from negative to positive, so that would be a min. Okay, and the last one, because we don't know what's going on, it just stops right there. We don't know. That's a neither either. Didn't mean to make that rhyme, but yes, neither either. Okay. Last question, find the intervals on which f is concave down. So again, it will be concave down when its derivative is negative. So when the derivative of this is negative. So this is a line positive slope. Okay, so that means it's concave up. This though is negative, so it's concave down. It looks like from -2 to 0. Okay, and then it stays. Okay, so that would be from 0 all the way to right here, okay, because right here its derivative has a horizontal tangent. So from 0 to 4, then it's positive, and then it looks like positive, positive, and then it looks like from 9 to 10. it would also be concave down. So again, I would write down concave down when the second derivative is negative, and that was again from -2 to 0, 0 to 4, and 9 to 10. All right.